Continuing our exploration into trigonometry, we are going to be working with trigonometric functions that are defined on the unit circle. And when you think of a unit, you're talking about one particular unit. The unit circle is a circle centered at the origin of 0, 0 with a radius of 1 unit. And this satisfies the equation of x squared plus y squared equals 1. Thinking about the unit circle satisfying the equation x squared plus y squared equals 1, let's use the point that's listed on the figure to the right, 1, 0. That's x of 1 and y of 0, so we have 1 squared plus 0 squared equals 1. And 1 does equal 1. That's true for any of these points that are, say, at pi over 2, pi, or 3 pi over 2. But what about some value in here? We'll investigate that a little bit further. We have mathematical functions that can model exponential growth, exponential decay, things that can model projectile motion, or functions that can model profit or cost or revenue, but we don't really have anything that can represent cyclical behavior, such as oscillations or orbits. And we're going to use the unit circle to help us do that. Remember that positive numbers wrap around counterclockwise, and negative numbers would go clockwise. So we can use the idea of counterclockwise and clockwise to help us define trigonometric functions as circular functions. So let's look at this circular function diagram on the right-hand side. Knowing that we have, let's say, instead of the value of theta equals pi over 4, let's call it t equals pi over 4. Let's say t equals pi over 2, t equals 3 pi over 4 and pi, and we're wrapping it around circularly around this unit circle. P is going to be the point associated with that real number t measured along the circumference of the unit circle from the point 1, 0. Taking this number line that you see here and just wrapping that number line around the circle like this. We can then use this unit circle to help us define trigonometric functions for any value. We're going to let P be the point xy that is associated with the real number t measured around the circumference of the unit circle. Notice the diagram on the right, we have defined these circular functions where x is equal to the cosine of t and y is equal to the sine of t. Well, think about the Pythagorean identity where you've got cosine squared plus sine squared equals 1. In that case, cosine squared is equal to x squared and sine squared is equal to y squared. So we can define the sine of t as y, the cosine of t as x, and the tangent of t as y over x. And then using the reciprocals where r is 1, we have cosecant, secant, and cotangent. Now, it's important to note what happens if the point is on one of the axes. So if the point P of xy is on the y-axis, then x equals 0, right? If you're on this y-axis right here, that would be at the points, there's a radius of 1, and so that would mean that if x is 0, we're dealing with y, and so we would have 0, 1, or 0, negative 1. Well, in that case, we've got some undefined functions that could happen. When you divide by 0, that doesn't work. So if p is on the y-axis and x equals 0, then tangent and secant are undefined because you have y over x for tangent and 1 over x for secant. So those are undefined. Let's talk about if p of xy is on the x-axis. If p of xy is on the x-axis, then y is 0, and that happens at the points 1, 0 and negative 1, 0. If y is 0, then cosecant and cotangent are going to be undefined. Evaluating trigonometric functions using the unit circle, let's think about this value of t. T here is an arc length measured from the central angle. Well, recall the arc length formula. The arc length S is found by taking the radius times the measure of theta, where theta is in radians. Well, in the unit circle, the radius is 1. So if I'm talking about the positive counterclockwise value of t, then the arc length s is equal to 1 times theta, or s equals theta. Well, s in this case is t, because that's the arc length that we're measuring. So t equals theta when we're talking about a positive value of theta. What about negative? What if I'm going in reverse? Well, r is still 1. And so we have s equals 1 times a negative theta since we're going clockwise. And so s equals negative theta in that case when we have t also being negative. So if negative t equals negative theta, then t still equals theta. And so I can use those formulas from above where the sine was y and the cosine was x to redefine the sine and cosine and tangent of theta. If theta equals t, then the sine of t is equal to the sine of theta. So instead of using t for some real number, we can call it theta because the measure of the arc length is the same measurement of the angle length on a unit circle. Let's recall our values for our 30, 60, 90 triangles. We had 1, root 3, and 2. And for our 45, 45, 90 triangle, we had 1, 1, root 2. We can use this idea to help us find the values for a unit circle. In this case, though, these values are not for a unit circle right now because the radius is not 1 in this case, it's 2. So how can I transform that so that I then get a unit value of 1 to apply this to the unit circle? If I divided through by 2, my ratio of 1, root 3, 2 then becomes 1/2 root 3 over 2 and 2 over 2, or 1. So in this triangle now, I get 1/2 root 3 over 2 and 1. And we do not use decimals. We leave these as fractions. What is 60 degrees in radians? It's pi over 3. 30 degrees is pi over 6. For our 45, 45, 90 triangle, I'm going to use the same idea. Our ratio is of 1, 1, root 2. I need to divide through by root 2 to turn that largest value into a 1. That means I have 1 over root 2, 1 over root 2, and root 2 over root 2 are 1, which is our goal. We wanted that longest side to be 1. But remember, we need to rationalize, which gives us root 2 over 2, root 2 over 2, 1 as our ratios. And what was 45 degrees as a radian? Was pi over 4. I could then draw a circle. On this circle, I could create some points at a specific measure of theta. So let's say I start here, and I have a measure of pi over 6 for 30 degrees. And then I do pi over 4, or 45 degrees. And then I have pi over 3 for 60 degrees. I could find what those point values are now based on the ratios that we have for 30, 60, 90, and knowing that the sine and cosine, remember we have this point xy, is the same thing as the point cosine of theta, sine of theta. Okay, so for a cosine of 30 degrees, remember 30 degrees is up here right now, so cosine is adjacent, which is root 3 over 2 over 1. That's going to be the x value, or root 3 over 2. How do I know it's the x value? Well, if this was my 30-degree triangle, Remember that opposite the 30 degree is 1/2. Adjacent to the 30 degree is root 3 over 2, and then the radius is 1. So the cosine of 30 degrees is root 3 over 2, and the sine is 1/2 over 1, which is just the y value. Remember, a unit circle is always 1, so you're just saying pull the x value, pull the y value. So the cosine of pi over 6 is root 3 over 2, and the sine of pi over 6 is 1/2. So that point on the unit circle corresponds to root 3 over 2, 1/2. Does that fall into the x squared plus y squared equals 1 identity that has to be true for this? Well, let's see. Root 3 over 2 squared plus 1/2 squared equals 1. Root 3 times root 3 is root 9, or 3. 2 squared is 4. 1 times 1 is 1. 2 times 2 is 4. Does 3/4 plus 1/4 equal 1? It sure does. 4/4 equals 1. That's true. So that point works. What about the 45, 45, 90 triangle? If I was to draw this, the x value, remember, across from each of these 45 angles is root 2 over 2. So the x value and the y value are both root 2 over 2. Because the cosine of a 45 degree angle is root 2 over 2, and the sine of a 45 degree angle is root 2 over 2 when you have that radius of 1. And then the pi over 3 value point is just the pi over 6 value reversed, because these angles switch from being opposite to adjacent and adjacent to opposite. So then we have point values for each of these on a unit circle, and we can do that. We can use these as reference angles and then apply the signs of being, okay, we've got an x negative and a y positive, x negative, y negative, x positive, y negative for this. And so we know that cosine is going to be negative here and sine is going to be positive, because when x is negative, cosine is negative. We know that sine is going to be negative and cosine is going to be negative here. Tangent is also going to be negative here because you have a positive and a negative. Tangent is going to be positive here. In the fourth quadrant, the cosine is going to be positive, sine is going to be negative. Think about it, x positive, y negative, and then tangent is also going to be negative. And then we can use these values from these 30, 60, 90, 45, 45, 90 triangles to help us fill in the values, or we can use the reference angles. Because we've got here, this value is 2 pi over 3. And then this value is 3 pi over 4. And this value is 5 pi over 6. And so we're dealing with reference angles. Notice that the yellows correspond, the blues correspond, the greens correspond. And so the yellow is going to have the same measurements, 1/2 and root 3 over 2, except the x is negative in this case. Same thing for blue. It's going to be root 2 over 2, root 2 over 2, but the x is negative. And with the green point, it's going to be root 3 over 2, 1/2, which is, again, just the opposite order of the yellow point with the x negative. And you can do that for the third quadrant and the fourth quadrant as well. It's going to be those same values for the reference angles. I'll draw them in for you. Here are the green points that are going to match up, the blue points that are going to match up, and the yellow points that are going to match up. And then you just have to adjust their signs appropriately, because remember, your reference angles are always in relation to your horizontal axis. So here is an image of a nice clean unit circle with all of the values and your degrees. So notice you've got negative x, positive y's in the second quadrant, negative x, negative y's in the third quadrant, positive x, negative y's in the fourth quadrant, and positive x and y in the first quadrant. And so that means that we've got the cosine is negative, your sine is positive, and your tangent is negative in the second quadrant. your cosine is negative, your sine is negative, and your tangent is positive in the third quadrant. Your cosine is positive, your sine is negative, and your tangent is negative in the fourth quadrant. And in the first quadrant, all are positive. And then you use your reciprocal functions, knowing that secant and cosine go together, cosecant and sine go together, and tangent and cotangent go together and are going to have the same sign. You can use this unit circle to evaluate all of these common values in pi or in degrees. And these are values when you get to calculus that you're going to want to memorize. You need to know them cold. You need to know that the cosine of pi over 6 is root 3 over 2.